Forces 4 newtons and 2 newtons act at a point. Which scale diagram shows the forces that have a resultant force of 4 newtons? So here's a simpler way of doing it if you kind of are still confused with vectors, is that this is a top view of, let's say, a box, which is right here. And there's 4 Newton force acting on it by, let's say, you yourself, you're pushing it. This is the top view, right? You're pushing it from here, and you can generate a force of 4 newtons. And let's say your younger sibling is trying their best to help you, but they're pushing it like that, right? So what will be the resultant force? So it's gonna move towards somewhere towards the right, probably over here, because you have some geometrical understanding of vectors. So the resultant vector will kind of add like this. You take this vector over here, and so the sibling will help you some way, right? Because he's also trying to push somewhat in the direction you're trying to force, you're trying to push. So he's not, it won't go directly that way, but he's not fighting against you. He's not nullifying your effort. So the resultant vector is going to go like that, right? And it's going to be greater than 4 because this is 4. And let's say if I put a compass ka tip yahan pe, and the pencil's over here, and if I try to make a radius, this length somewhere here would be 4, and this is more than 4. This extra length is, it's probably going to be 5 or 6, right? We can see that happening. So this is not, the resultant is not 4, right? For the second one, we do the same thing, right? We know the resultant vector is going to be here, kind of like that, you know? And that does look like 4. We do the compass thing. This length over here, this length over here seems very close to 4. How do I know? Because if I take my nib of my compass here and the pencil here, it can trace it all the way here. It can make an arc like that, and it'll stop over here. So this length, I'm pretty sure, is also 4 newtons. So that's our answer. The resultant is indeed 4 over here. Weird how it turns out like that. Using the Pythagorean theorem, you understand you can calculate the exact length of this vector, and you'll know the hypotenuse for any right angle with sides, you know. The hypotenuse, in other words, let's say, is actually always greater to the length of the sides, because that's the hypotenuse is the longest side of a right angle triangle. Said right angle triangle is this one. And for the last one, they'll obviously negate. They're in one line, so it's easier to do the math. The equivalent vector over here is just 2 newtons to the right, because you're trying to push 4 newtons towards the right and someone's trying to counteract it by 2 newtons. So the effective vector is 2 newtons towards the right. So B is our correct answer over here. B. How does an oil-fired station differ from a nuclear power station? Now, one thing to note is that the only way to generate electricity, correct me if I'm wrong, is either through solar cells, which is only used in solar electricity, right? Like solar, why am I drawing a block over here? I don't know. Like solar cells, right? You've seen it on top of calculator. They don't have a turbine in them, obviously. And there's specific cells when exposed to light from the sun, they can change that into electricity, right? So they work like that. They're sensitive to the sun that way. The only other way to generate electricity is by spinning a turbine. Now, a turbine you've probably studied in detail is just magnets around a wire, and let's try drawing a turbine. That's my impression of a turbine. That's a turbine to me, right? And no matter what you're using, any power station is trying its best to turn a turbine. So most of what they try to do, they take water in, and whatever the fuel is, they use the fuel to heat that water, turn it into steam, and push it through. Like dams won't use water and turn it into steam. They use the pressure of the dam and pass all that high pressured water through the turbine, and the turbine spins, and spinning of the turbine will generate electricity, right? In an oil-fired power plant, or fossil fuel power plant and a nuclear power plant, they're very similar. The entire mechanism is the same aside from the burning of the fuel. In an oil-fired power plant, there's like a boiler, which, well, let's make another rectangle. There's a boiler, and the fuel will go in the boiler, and steam will come out trying to heat the turbine, right? And the fuel is only different for a nuclear power plant and an oil-fired power plant. Now, their boiler design might change a bit depending on how to cater the different types of fuels, but more or less they're kind of similar, right? The principle is the same, right? So gases are emitted by hot fuels are emitted into the atmosphere. That's one thing that's different from a nuclear power plant, because a nuclear power plant is consuming uranium, right? And gases aren't produced, but other things are produced, but not gases. But in a fossil fuel-based power plant, gases are produced, of which some of them are carbon dioxide. So that's one thing that's different, and the answer is A. Steam is produced in a boiler using hot fuel. Well, that's true for both nuclear. Like, nuclear energy isn't magic. A nuclear power plant is essentially an oil power plant, but instead of using oil to burn the water to heat it up, you use a mini, slow exploding nuclear bomb, essentially, right? So it doesn't produce any gases, but the entire mechanism is the same, and it does produce steam. Have you seen those huge chimneys for nuclear power stations, the big ones? They're just throwing out steam. It's not pollution, and it's not even radioactive, right? Because that's dangerous, right? Those big ones, they're just throwing out steam. Okay, steam is produced in the boiler using, that's true for both. Hot steam is used to turn the turbine. We just talked about that. Turbines are used to drive that's true. So it's a steam turbine, right? Steam turbine. So the correct answer is, again, A. The best way to explain this is that you have to have a little understanding of maths, right? Here's an equation for a straight line. Y equals to mx plus c. Now, normally for straight line graphs, if they're starting from 0, there is no c. So it'll just be y equals to mx. So a straight line graph would be something like this. F equals to ma. So if you try to plot a graph that's force and acceleration, the gradient will be constant, and the higher the force, essentially, the more the acceleration. And the mass would depict, the larger the mass, the higher this curve will, or line will be, meaning more force is required to increase the acceleration by a small amount, right? And the lower the mass, the line would be here somewhere, meaning even a little increase in force will increase the acceleration by a lot, and that makes a lot of logical sense as well, right? But for pressure, that's not the equation we normally see. What equation relates pressure to area? Because that's the graph drawn. That is the graph drawn. Pressure is linked to area by force, right? Pressure is defined as force per unit area, force applied per unit area. And this graph, so to speak, the gradient is going to be force, but there's no gradient because it's not a straight line. It's a pressure is proportional to area graph, or y is proportional to 1 over x, that sort of graph, right? Or y is equal to 1 over x. And if you've seen those graphs, they'll look a lot like this, right? You can easily tell, even by logic, that the larger the area, the pressure will be lower. So it makes sense the graph is going down, but it will let go constantly or do a weird thing. So either you're familiar with this sort of equation, and you should be at this point. It's nothing too complicated. Or you could just plot 3 points and figure out that it's not a straight line, right? Or you understand that it's not a straight line equation and it's definitely N, rule out C. And go for the correct answer, which is D. Right? That's the math way of solving it. The other way would be, I guess, a little more intuition, or being familiar with this graph, pressure and area graph, already by looking at examples in the book and notes and whatnot. That would be the other way, but that's more towards rote learning rather than understanding what a different graphs are like. So that's your answer, D. Each tire of a car has a 100 centimeters square in contact with the ground. The car has a mass of 1600 kilograms. The weight of the car is equally distributed amongst the 4 tiers. The gravitational field strength is, well, what is the pressure exerted on the ground? So one tire, that's the contact area of the tire. And you have 4 tires, and it's trying to figure out, like, hey, it's trying to ask that, what is the pressure? Now let's go to our favorite view. This is the top view of my Model S, right? Now I'm only representing the area, which is this area, which is in contact with the, that's such a horrible pen. The area of the tire in contact with the ground. That's what I'm only trying to draw. Should have drawn the body just a bit more. But yeah, I think we're happy with it. Now the force occupied or sustained or supported by this area is actually the weight of the car, which is actually force equals to mg, because we're talking about weight. I could have used W, but I want to see this as force. The mass of the car is 1600, and the gravitational acceleration is 10, which makes it 16,000 newtons. And they're asking for the answer in Newton per centimeter. So to calculate the pressure, calculating the pressure is going to be pretty simple. It's going to be force over area, where the force is 16,000, sorry, and the area is actually 400, right? 400 because there are 4 of these 100 centimeter squared contacts. So 4 tires, essentially. Fancy way of saying tires. 0 zeros, 160 divided by 4 is going to be 40. So this makes it 40 newtons for every centimeter square, right? And that makes sense. And the correct answer is, C. We have a diagram that represents 4 thermometers, and we're trying to figure out which has the greatest sensitivity and which has the greatest range. So the greatest range would be a thermometer which has the greatest, last point, like the difference between the, the largest point and the smallest point is the most. So this has a range of 25 centimeter cube. Why not? Let's go with centimeter cube. Okay, this has a range of 10 centimeter cube. That's the difference of 40 and 30. This has a range of 250, whereas this has a range of 200. It is our that we decree which has the greatest range. How fitting. Range, the greatest range is of R, and the greatest sensitivity is of, that'll have the most most spread out numbers. So this length is spreading out 25 Celsius centigrade, right? This is spreading out 10 Celsius in this entire length, 250 and 200. So Q should have the greatest of all sensitivities. What a QT. All right, so Q and R are our answer. Let's check out the next slide. Q and R. Correct answer is C. What happens when a solid is heated and expands? The molecules do not change size in the space. Some of these questions. Why would they change size? The molecules do not change size and the spaces between the molecules becomes larger. Yes. Okay, I'll go with that. Yes. The molecules expand and the spaces between the molecules become larger. Oh my god. And smaller and smaller. Okay. So, yeah, the correct answer is A. The diagram shows the path of two rays from the top of an object through a lens. The object is viewed from opposite sides of the lens to the object. How does the image compare with the object? Now the image is going to be formed somewhere like that. So this line is pretty horizontal, that won't change. But over here, the observer will see, you know, like when he sees in this line how this ray is coming out in this line, he'll see the image again, right? So what he ends up seeing is, if we trace that line all the way back, something like that. Okay, the word for worst line drawn is goes to me. Okay, something like that. Still not ideal, but okay. And the image will be like that. They'll see that. So what is the image now? The image will be smaller in the same way. The correct answer is D. All right. The diagram shows a loudspeaker that is producing a continuous sound wave of frequency 200 hertz in air. Which diagram best shows the sound wave causes a molecule at point P to move during 1/2000 a second? So in 1/2000th of a second, so 2000 hertz means it's oscillating 2000. So that would mean it'll complete one complete oscillation, right? Okay. And now, which diagram shows the best and how sound wave causes the molecule? Okay. So I think taking a closer look, B and A are identical, but they're halves of each other, right? Like this is double the movement where P is just one. So you can narrow it down to A and B just like that, because how similar they are versus these two, which are not similar. This is saying the P will move kind of like that. This is saying P would move up and down. So the sound coming out of this is actually, what is sound really? It's just energy is coming out in the form of compressions and opposite of compressions, right? Like expansions, I guess, right? So there's a word for it, but like, okay, just compressions and not compressions, right? So what's going to happen to P? So P will actually kind of be vibrating back and forth depending on the, because it can't really move up and down. And a better way of understanding this is how a speaker, have you seen a speaker close up? It kind of vibrates back and forth, you know, kind of back and forth. That's like coming out, going back in. So it's vibrating back and forth depending on the sound it's trying to make. So it's gonna push it back and bring it forth. And the question is it going to push it back and bring it forth in that amount of time, or will it only be able to push it? That's a real question. It can't really move it, you know, perpendicularly to the sound. And same for D. So C and D are out. D would be a good choice, good answer if this was a waterway. So B would go like, woo. Okay. Anyway, so the sound is coming in. So in 1/2000th of a second, it should do one complete oscillation. 200 hertz means it's oscillating, doing complete oscillations in that amount of time per second. So in that time, this should complete one complete oscillation. So the correct answer is, without a doubt, is A, right? A copper wire X has resistance R. Another copper wire Y has twice the length and half the cross-sectional area. What is the resistance of Y? A copper wire X has a resistance R. Another copper wire Y has twice the length and half the cross-sectional area of X. Okay, if this is R, let's call this wire 1, and I'm gonna call this wire 3. Let's say there was a wire 2 which only had the same area A but double the length. So somewhere in between wire 1 and 3, right? Double the length but same area. If wire 1 had resistivity R, now I'm saying this because I don't remember the formula for resistance using resistivity. Actually, I do know it, but I'm just trying to make a case where you can still solve it just by pure logic, and the formula itself is just pure logic, right? Okay, let's say you had a wire which had area A and the length was 2L. What would its resistance be? BE, right? So wouldn't it be double? It's kind of like taking these two wires, joining them together. So whatever if the resistance dropped from this current is R, for the second wire it's going to be R as well. So that's R and R. So it's going to be, the resistance is going to be 2R, right? Yes. Okay. Now what happens if you go from 2 and go to 3, but you half the area? You like cut the wire in half essentially, right? What's going to happen then? What happens to the ease of electron flow? Do electrons flow more easily if the wire is thinner, if the area is thinner? Think about traffic. If you're on, you know, Shah Faisal or some main highway and it's a 4-lane road that turns into a 2-lane road, what's going to happen to the traffic? It's going to increase. So the resistance will also increase. So from 2R, it'll actually double because it has half the support, and from 2R, it's going to turn into 4R. And the correct answer is D. Now, this sort of question you can solve in under 30 seconds to go like, oh, double the resistance means, double the wire length means double the resistance, and halving the area would also actually double the resistance again. So R times 2 times 2 is 4R. You did it probably in 13 seconds rather than 30 seconds. Answer is D. A horizontal beam of electrons passes between two poles of a magnet. In which direction is the beam deflected? So you have a beam of electrons going. Okay. Now understand one thing is the current, if it has a direction like that, the electrons are actually moving against the conventional current. We call it conventional current because earlier we thought that's how the whatever is responsible for electricity is moving, but later we found out, oh, it's the opposite, right? Let's say this beam of electrons was actually, because it can flow in a wire, this beam of electrons was actually in a wire. So in this wire, If the electrons were traveling towards the right, which way will the current be? Towards that. That's the worst eye I've ever drawn, and I will undo it, and I will make a better eye. That. Yeah, okay. Take it. So at this point in time, you can use the left hand rule to your advantage. Left hand rule. The left hand rule will tell you the direction of the force generated, right? So if this hypothetical non-existent current, which is actually there, like, you know, the convention is highlighted, is actually highlighted, and if you use your left hand rule, so the middle finger tells you, you place your middle finger in this direction and your index finger goes top to bottom. So let's redo that. So if you place your left hand and your middle finger MF is pointing like that, and if your index finger is pointing like that, north to south, IF, right? Which direction is your thumb facing? Let me kind of work that out. Okay, so it's facing towards me out of the page, right? It's facing towards me out of the page. So it's gonna kind of come like that, come out like that. That's your thumb finger, right? Thumb, okay, let's go for TH, right? That's where, and that's the force on this electron, right? Does that make sense? The force generated on this electron is going to come out of the page, so this electron beam will out of the page, not downwards, out of the page. I can't really draw it. See if we can. Kind of like, okay, it looks like it's going down, but it's actually, you know, three-dimensional. You know what I mean? It's kind of coming out of the page. Okay, out of the page, the correct answer is B. So erase that little dot. Yeah, and why did we choose to do it this way? Now, what happens is, you know your left-hand rule. Left-hand rule came before probably the understanding of electrons. What's happening is you highlighted the left-hand rule by saying that your left-hand rule was invented using the conventional current, right? So your current is essentially, your conventional current is actually the reverse direction of how your electrons are flowing. So you can apply the same logic over here and figure out in what direction is the force being generated if you use, because you already know it, right? You don't want to learn something new for just every question. Don't learn something new, just use the same logic. If a wire carrying a current like that is going to move out of the page like that, because each electron is being pushed away because of the magnetic field, what is going to happen to the same beam of electrons if only the wire was absent? So answer is B. This question is in two parts. So the half of the part is on the next page. Okay, a loudspeaker and a microphone are placed in front of a wall. The loudspeaker makes a sound which is detected by a microphone. This microphone is also connected to an oscillator, which we'll see in the next page. The microphone, okay. Each division on the screen is 0.01 second, 0.01 second, right? And the microphone detects the original sound and the echo. So like bloop, bloop, right? The first bloop it detected was from the loudspeaker, so it was instantaneous. And the second one was, so essentially I'm guessing we have to find the distance, this distance D. Now one thing, because we have to find that out, is you have to understand that the sound went like that to like that. So it actually ended up traveling 2D, two-dimensional. Okay. The distance traveled by the sound was 2D, and the formula for, okay, let's back it up here, back it up. The formula for sound traveling a particular distance is or let's go with dist over time. So the velocity is, the question says, is 300 meter per second for all sounds and sound kind. And the distance traveled is actually by the same sound is 2d, and we can measure how much time it took by counting. So it's kind of like the sound is spreading over like one entire thing. Which do we count? The sound, like which cell do we count where the sound is starting? So the sound is starting here, here, and it's counting, stopping here, right? So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. And each of the cell is 0.1, and you have 8 of these 0.01 second cells, or divisions. So the time it took for this sound to travel is 0.08. So 0.08. Doing the math, D will come out to 12 meters. Easy question. And our correct answer is now B. A circuit diagram shows a variable resistor R connected in parallel to the lower half of a potential divider. Okay. The resistance of R is increased. This is increased. What happens to the 2 voltmeter readings? Variable resistor R connected in parallel to the lower half. I'm assuming these doesn't really matter. Okay, if you increase this, what's happening to this total resistance of these two parallel things? I'm guessing it should increase, right? Okay, the parallel resistance formula is 1 over R is 1 over R1 plus 1 over R2, the whatever's in parallel. So if this value increases, this entire value becomes smaller, right? So this entire value, this addition becomes smaller, and this becomes smaller. But if this is becoming smaller, it's actually inverse fraction, right? What's happening to R is R, the total resistance, is actually getting bigger, because 1 over R is getting smaller, and 1 over R, like this is the sum of the entire thing. So resistance of this entire thing is increasing. So think about it this way. Let's remove this resistance, and let's say you had 2 resistors and this resistance was getting higher, because essentially these 2 resistors combined are increasing the resistance. What's going to happen to V2? V2 is going to get larger, and because there's a finite amount of voltage coming in and that's being divided, this is going to decrease. So this will get larger because there is more resistance now than this. So V2 will, I'm really enjoying the pencil for some reason. So there's V1 and V2. We figured out that the V2 will increase. So V1 in essence will decrease. And which option is telling us that? Is V1 will decrease? Oh, that's not it. Decrease and decrease. So increase and increase. The correct answer is B.